Look at this example here. First, we're going to look at what we're given. We've got a 12-tooth driver gear. Okay, so this small gear here is going to be my in. We have a 36-tooth driven gear. So this larger gear is going to be my out. I'm also given 100 RPMs. I know that if I use a 393 Vex motor at full power, it's going to have an RPM of 100. So say I'm needing to pick something up that's a little bit heavier, maybe that 100 RPMs is not going to give me enough torque so that I can raise it or get over maybe a hump, then I'm going to need to hook up gears to it so that whatever this is attached to will have more torque. So this is something that you might see whenever you're building the robot. So let's look at the equation. I've got number of teeth and I have RPM. So I'm going to use the equation that is in number of teeth out over number of teeth in, and I'm going to set it equal to my angular velocity in over my angular velocity out. Okay, plugging these values in, my out is 36, my in is 12. Just looking at that, I can tell that I have a gear ratio of 3. I set it equal to my angular velocity in is 100 RPM, and I'm trying to find my angular velocity out. All right, so 100 times 12 divided by 36 gives me 33.3 RPM. Now let's look at this second example. I still have a 12-tooth gear and a 36-tooth gear. But this time I have as my driver gear the large 36-tooth and my driven gear as the smaller 12-tooth. So my in is the larger one, my out is the smaller one. And we're also given that we have 5.0 foot-pounds on the smaller gear, which is our driven. Okay, so the equation that we're going to use this time is still going to be in, out, over number of teeth in. But this time we're going to use torque. Torque out over torque in. So my number of teeth out is going to be 12 this time, and my number of teeth in is 36. I'm going to set that equal to my torque out, which is 5.0 foot-pounds, and I'm going to solve for torque in. So we have 5.0 times 36 divided by 12, and that's going to give me 15 foot-pounds. All right, so notice 15 is larger than 5. So we're starting out with 15 foot-pounds, and then the smaller gear is only ending up with 5 foot-pounds. So as you can see then, we are trading the torque for speed, because if we did this again with speed being our angular velocity, we would notice that our smaller gear would have a higher speed, and our gear ratio is going to be 1 to 3 this time, which is a smaller number. So the smaller the gear ratio, the higher the angular velocity, and the smaller the torque on the out gear. And sometimes you're going to hear the terms geared up and geared down when you're building your robots. If you're gearing something up, you're actually wanting to add more speed. If you're gearing it down, then you're going to want less speed and more torque. And it's kind of backwards, I know, because we talked about the higher the gear ratio, the higher the torque, and the lower the gear ratio, lower the torque. And that's why I want to bring it up here, because a lot of times when they're talking about this, they're wanting to say more speed because you want that so that you can get to something quicker. Now, for lifting something, especially with the arm, you're usually wanting to gear it down. So if you hear that, realize they're talking about speed and not the actual gear ratio, okay?